Hello, my name is Paisley Code. I'm going to be discussing DIPS, Debug Intermittently Powered Systems like any embedded system. This is a paper from Delft University of Technology, and this is a hardware tool or hardware and software tool which can be used to debug intermittently powered systems, since they can introduce some unique challenges that aren't necessarily available in other embedded systems or in other like regular software debuggers that you can find in most popular IDEs. So first, we're going to discuss intermittent computing background. So a key feature of intermittent computing is in the name, an intermittent power supply. So essentially, it does not have a constant power supply, and it takes power from the surrounding environment in order to perform certain operations. So essentially, as you can see from this diagram, it sort of powers up its stored energy, system turns on, it uses up that energy, and then it sort of powers up again. So it sort of has the cycle of going up and down, depending on the varying energy which it receives. So this has to only use environmental energy. So there's no batteries and no constant power supply in general. So this has to exclusively rely on external energy or from the environment, which when it comes to cases such as RF or radio frequency energy, then is going to be super inconsistent. So that's sort of something to take into consideration. So there are three common tasks, which this paper explores. In the context of using the debugger, were essentially SenSys. So this would be using any kind of sensor which is attached to it. I'll get into a little bit more detail on that later. And then there's also performing computations on the data, such as encrypting, decrypting, or processing any of the sense data that it takes in. And then there's also transmitting the data, so sort of sending it out, whether that be to an external server or some other tool. So you can also see here that there's a process of restoring and taking a checkpoint between each of these stored energy consumption areas. So this is another key feature of intermittent computing systems, where it essentially sort of needs to restore what it was like before it shut off, and then take a checkpoint near the end. So it's sort of similar to when a different type of device shuts down that doesn't necessarily have intermittent computing capability. It still needs to restore what happened before. However, here it sort of takes into consideration that's going to happen a lot, so it sort of can pick up right where it left off with minimal consequence. So here we have the hardware of intermittent computing. So as I mentioned before, there's no battery, and it exclusively uses capacitors or supercapacitors. And one main benefit of these are that they are smaller, cheaper, and less polluting than batteries. But it also requires less maintenance, since you don't need to replace the battery over time. You can just keep repowering up that capacitor based on the environmental energy. So you can sort of leave an energy harvesting tool out in the middle of nowhere, and it'll keep running. You don't need to constantly check up on it. Another tool is the microcontroller, and this is the thing that's sort of performing the computations. And there are also other potential peripherals, and these can include screens, sensors, speakers, lights, basically anything from the outside to sort of display information to the user, or also certain sensors, such as temperature sensors, camera sensors, or basically just any kind of sensor that can take in data from the surroundings. Next is some kind of power source. In this case, when I mean power source, I don't mean anything necessarily directly connected to the device, but sort of the environmental energy that it's going to take in. So for example, if you have an intermittent computing device that's running on solar power, you sort of need to put that in a place where the sun is. So you sort of need some kind of power to be available. Or in the case of vibrational energy, you might want to put it in a place where it's going to be moving a bit more. Next, there is also the energy harvester. So this is sort of the tool that's going to be harvesting that energy and powering up that supercapacitor with the environmental energy. So these are all factors which are going to be explored by the debugger, or some of these are going to be factors which are explored by the debugger in order to ensure that we're able to properly debug whatever program we may want to create in the future. So here are some considerations for intermittent computing. So these are some methods of in order preserving data when there is an outage. So one way is to take multiple steps when a power interrupt occurs. So essentially you need to resume operation when the power returns, so it can't just shut off and then be done with everything. And then the memory state must also be restored accurately. So essentially you can't just have the power go out and then restart from the beginning. You also need to restore the memory state as well, and have it be done in an appropriate way. So these are two features which a debugger is going to sort of check out for and ensure are all functioning as intended. So there are a couple of methods for doing this, which DIPS does take into consideration both of them. And these can include checkpoints. So in the paper Wario and Ratchet, these two use checkpoints in order to preserve sort of the memory state when there is a power outage. And then there are also atomic blocks, such as Chain and Alpaca, which sort of use atomic blocks in order to sort of keep track of certain systems. And these are sort of similar to checkpoint systems, at least in my interpretation of them, where they sort of like take a checkpoint before and after each block, or after each block, in order to keep track of what's currently happening within this paper. And what I find kind of interesting is that doesn't seem to be any like direct affiliation between the writers of this paper and any of these tools, which I know I did another analysis for one of the tools listed here, and I find it interesting how like interconnected it is with all the other tools that are created, while this paper doesn't really seem super connected with them, which I thought was rather interesting. So next, there is some prior work on debuggers. So there's only really one, which is EDB, and this is prior work with debuggers specifically for intermittent computing devices. There are plenty of debuggers for other types of devices, such as GDB, which DIPS does eventually use. So there's only really one for intermittent computing, though, which is EDB, and this code needs to be instrumented manually, so essentially the user needs to sort of implement the code themselves, which can be rather difficult or provide a really high barrier to entry. And each new breakpoint also requires a new compilation, so you can't just like add multiple breakpoints in one point. You sort of need to recompile the debugger in order to add these new breakpoints. There also is not a simple user interface, and it does not allow for replay. So if you're having some kind of energy replay, you can't necessarily use that. And it needs to be powered with environmental energy. So it's all just like live in the moment. So for example, if I want to debug something finicky, or if I want to debug something that may have caused an error in a regular non-intermittent computing device, there's not going to be a very easy way for me to do that. It can also be rather time-consuming, partially due to the prior issues. And another major issue would be that it can also mask right after read errors. So you can see here, if you place the checkpoint in a certain spot, then it won't actually be able to detect the right after read error in this case, which would kind of defeat the purpose of debugger, since you want to use it in order to detect these errors. So next, there's also what the current debugging space sort of looks like. So essentially a lot of pre-existing software outside of intermittent computing sort of assumes that you have a constant power source. And also a lot of intermittent computing devices mainly use C code, which fortunately there are pre-existing debuggers which work with C code, since it's very common. So a lot of debugging is also mainly with GDB and also mainly in an IDE as well. These are two tools which are sort of used to perform debugging in the common space. So next, there are also different types of intermittent computing bugs and also non-intermittent computing bugs. And DIPS hopes to sort of help out with both of these potential bugs. So one is common bugs. These are essentially bugs which you can find in any kind of system. So you can see here I's in the while section, and then the J's being incremented, so it's I's going to be an infinite loop. So basically just not necessarily minor bugs, but common bugs outside of intermittent computing devices. However, there are three unique intermittent operation bugs, which are essentially sort of only for intermittent computing devices, or only bugs that will be encountered in that circumstance. So one is peripheral restoration bugs. So this is essentially an inaccurate reinitialization after a checkpoint restoration. So if you remember the diagram from before, the step is restore, run your process, and then take a checkpoint at the end before the power runs out. However, if you restore the process incorrectly, you're going to have a couple of issues when you're starting it up. So you can see in this example, it sort of takes the real-time clock start, and then it sort of uses that real-time clock to run a while loop. However, if there's a power failure and we're not able to initialize that clock, there's going to be a lot of issues because essentially RDC is going to stay constant or be set to the incorrect value. So it's not going to work in this case. So this is also really crucial if you're sort of measuring an environmental variable, because if you're not setting up your sensor correctly, then you're not going to be able to read the information correctly at all, or it's either going to be incorrect or not going to be able to read it at all, and then you're sort of wasting a power cycle. Another potential bug exclusive to intermittent operations is memory restoration. So this is if there's like a wrong checkpoint placement. So a lot of memory restoration uses double buffering in order to sort of keep track of changes while keeping the checkpoint intact. So if a power failure sort of happens at the wrong time while you're sort of balancing these two different buffers, then the memory preservation won't necessarily be correct, and it's going to cause issues for the section. And another common issue, which is sort of almost exclusive to task-based systems, is essentially when there's like checkpointing, which happens between tasks, but they aren't necessarily connected. So in Alpaca, each task sort of flows into the next task. So at the end of each task, you need to call a separate task right afterwards. So if you sort of accidentally make an error with that, or never call a specific task which you thought you would, or I think you can also set like a successor task. So if you name a task successor and then you sort of have that collision there, I'm not sure if they already have protections against that, but if you sort of have some kind of issue similar to that, then you're going to have an incorrect task sequence. And as you can see here, you're sort of sensing, then computing, but you never actually reach the transmit task. Computing just goes straight to sense. So in this example, it's sort of like you're never going to reach the desired task which you want. And this issue can also occur when defining volatile memory for each task, since volatile memory can sort of store the current task. So if you're at a certain checkpoint and you're going to start at a certain area, then that's sort of the area of memory which is sort of keeping the track of that. So if that's going to be incorrect, then you're going to start at the wrong line, and that's also going to cause issues when you're sort of starting your program back up again. So these are some common bugs which are sort of, I think there might be some circumstance where they aren't exclusive to intermittent computing, but these are more so for intermittent computing. So next, there are a couple of challenges which debuggers hope to solve, and this is what DIPS hopes to resolve. So one thing is that it sort of requires external hardware in order to do everything that is necessary. So for example, an intermittent computing device does not have a stable power source. So if you sort of want to check, hey, would this work if I don't have intermittent power source, or if I could rely on a battery for this code, would it still work? You can't necessarily answer that question. You sort of need to exclusively assume that. So having external hardware can help say, okay, there's a battery attached. Now I know that's going to work. If consistent power is given, the problem is probably one of those intermittent computing bugs instead of a regular bug. Next, it also needs to have the ability to replicate an intermittent power source instead of constantly being next to one. You can sort of see how it would work in a different circumstance or using a different type of power source instead. So here they have this chart which compares EDB, which is the debugger I mentioned earlier, which is the current or current for the time debugger for intermittently powered battery-free embedded systems. That's a quote from the paper, if you couldn't tell. So that's sort of like the current status quo. And then there's also JLink, which is a popular debugger for embedded systems, which do have batteries in them. So as you can see here with JLink, it has a lot of these features except for MSP430 support and software testing, but you can also notice that it doesn't have the two energy-focused ones, and that's because it's not for intermittent computing. However, it is still useful for everything else. EDB, however, does have energy breakpoints, so you can actually perform some intermittent computing focused operations on it. And you can also see here that it has a bunch of separate tools which are useful, and also uses GDB, which is a popular debugger. So how exactly does DIPS solve these flaws or drawbacks with previous debugging tools? And based on that prior list, I'll go back to it real quick. What new features would you necessarily want to add here that would be useful for an intermittent computing system or a non-intermittent computing system? Yeah, so next here, as you can see, they believe, or I guess DIPS does fulfill all of these requirements. It's able to set energy breakpoints, software breakpoints, hardware breakpoints, and perform all of these operations that are necessary and useful for any kind of intermittent computing debug system. And I'll explore some of these in a little bit more depth later on. What exactly does DIPS do, whether compared to previous debug systems or just in general? What tools does it provide in the debugging space? So you can see here, it has multiple different features. I'll only explore a couple of them since some aren't necessarily super debug focused. But for one, it has memory restoration. So for instance, if you want to restore a certain area in memory, and it can also check the peripheral state. So sort of like checking the state of the certain peripherals. And most importantly, in my opinion, it has IDE support. So you can sort of use an IDE to visually see the code which is running, which I think is really, really useful for any kind of debug system. It also has a hardware debugger, which is sort of split into two parts. One which is sort of more for regular debugging use, and another for specifically for intermittent computing devices. And there's also an energy emulator, which is sort of exclusive to intermittent computing devices since energy use is such a primary focus for them. So first, we're going to look at hardware-based debugging. So essentially, this means that you're able to use the hardware debugging features of a microcontroller, and these use GDB. So these are essentially sort of, it uses like a piece of hardware, so it has like an actual board which connects to the intermittent computing device, and then that is sort of able to perform these hardware debugging operations on it. And this is a battery-based device since you need to be able to provide constant power to the board in order to perform all of these operations. So one key feature here is sort of regular, this is sort of the regular debugger, and it has a bunch of different features which can be used when debugging. So one key feature is halting, so pausing execution at any point. So sort of like if you detect there's an issue, this is similar to other debugging tools, so this might be a bit redundant, but sort of able to pause execution at any point when you detect an issue at a specific point. Next is the ability to read and write to memory, so you can sort of access the memory of the microcontroller and sort of edit specific parts of it if the values may not be correct, or if you want to go and access this one specific part of the code that might not necessarily be easily accessible in general. Next is setting breakpoints. This is a really classic debugger tool where essentially you set a breakpoint, then you're able to sort of run it, have it stop run at that point, and then check any problem areas. Another feature is checking lock points, another debugging tool where you're sort of able to monitor different changes in memory and sort of see, okay, is this memory address being used properly? And this can be especially crucial for sort of detecting changes in volatile memory in one of the debugging processes mentioned earlier. So while these are very common debugger tools, they can also have an extra added use in the intermittent computing space. So this sort of makes these tools especially important since they're not only useful for regular debugging, but also for debugging intermittent devices, or intermittent computing devices. So next is energy neutral debugging. And this is split into two parts, which is attached, where you sort of have a constant power supply. So this sort of gives flexibility and make the device seem like it's part of a normal embedded system with no intermittent computing. So this means you can sort of differentiate between two different types of potential problem areas. So you can sort of see, okay, is this a problem with intermittent computing? Am I not managing that correctly? Or is it a problem with my legitimate code? And it sort of allows you to sort of check that, okay, it runs with a constant power supply, so it has to be a problem with how I'm managing these intermittent computing functions, or how I'm like restoring or saving my checkpoint. Now another system is detached. So this sort of has a conditional power supply where the device uses energy harvesting until a debugging operation is used, such as a hardware interrupt or any of these tools mentioned earlier. So if any of these are used, then it switches back to the power focused, or then it switches back to the infinite, in quotations, supply of power. So this sort of allows it to emulate. Now it's not quite exact since you still are able to switch back and forth, but it is pretty close and sort of emulates some of what EDB did before by having that intermittent computing system in place. So next up we have energy emulation. So this essentially allows harvest energy into the supercapacitor, and the harvest sort of determines when the voltage regulator powers on and off. So this sort of like is a way of recording the amount of energy that's supposed to be put in. And it also allows for energy replay, so you're essentially able to replay previous energy absorption tools. So essentially you're able to take a record of sort of the environmental energy in this one area, and then you're sort of using that to replay it for this emulation tool. So it also allows development to sort of take into account different types of realistic scenarios that you may potentially encounter. So this mimics the buck boost converter and a storage capacitor, and this is from Texas Instruments. So far, this is the only specific one they have, and they claim that it's sort of like the most common one, which means that they will necessarily need to do the one. However, they also have synthetic emulation, which sort of emulates other common, which sort of emulates almost random arbitrary signals from external areas, such as like sawtooth waves or sine waves. And this helps with stress testing. So if there's like random signals being put through, you want to be able to manage those as well, instead of very specific ones. So next up we have the PC interface. As I said before, I think this is probably one of them. I don't want to say one of the more useful tools, but I think I'd really struggle to do debugging without some kind of visual interface in some circumstances. So I think being able to have the integrated developer environment, and especially the emulator graphical user interface, in order to look at that as well. So you can see here that you sort of have this hardware section here, where you sort of have the energy emulator, the hardware debugger using GDB and the programming tools, GDB server and the programmer tools. Then you also have the synthetic and virtual emulation as well. Next up, we have automated software testing. So this sort of is ways of testing the software within the device. And so first there's memory restoration, which sort of can check the memory restoration correctness through the power failures. So it essentially allows the user to check if memory restoration is successful by checking the current memory values before and after the checkpoint is restored. So you're sort of able to see, okay, was this restored correctly? Are these values the same? Next, it also checks sort of the same exact thing, but for the peripheral settings. So you're able to see, okay, are those restored properly after a power outage? Yep, so based on what I explored before, you can sort of see all of these things were sort of covered by DIPS. Now there are some parts which I did not necessarily mention, like the ARM and MSP430 support, and you may need to get a little bit more detail from the actual paper itself. I did not go super in depth, I'm just sort of giving a brief overview of some of the features that DIPS provides. So overall, I thought this was a really interesting tool, and I definitely think that it would be very difficult to sort of do debugging without any of these tools. So I guess my question for you all is, what are some other features which would be useful, or are there any other embedded systems tools that would require a specialized debugger similar to intermittent computing systems? All right, thank you.